This lesson will focus on the Class B single-engine performance requirements for the en route and descent stage of flight. Essentially, the en route part of the flight is considered to be from 1,500 feet above the airfield from which the airplane has taken off to 1,000 feet above the destination airfield. Although the CAP 698 manual does show the en route performance requirements, these requirements are scattered through the document, which does not make for ease of reference. Therefore, it will be more convenient for you to refer to the original regulations published in JAROPS 1, as illustrated here. This regulation states that an operator must ensure that the aeroplane, in the meteorological conditions expected for the flight, and in the event of engine failure, is capable of reaching a place at which a safe forced landing can be made. In order to be able to comply with the rule you have just seen, an operator has to know certain details about the route to be flown and the performance of the aeroplane. First of all, of course, for any given route, an operator must know the safe forced landing areas. On screen is a bird's eye view of an example flight from airfield A to airfield B, with the locations of safe forced landing areas. The next detail that the operator needs to know is whether his aeroplane will be able to reach these areas if the engine were to fail whilst en route to airfield B. Whether or not this is possible will depend on two things: the altitude chosen for the flight, and the descent gradient of the aeroplane following engine failure. If these two parameters are known, it is possible to calculate how far the aeroplane will travel following engine failure. So let us work through an actual example. Let us assume a cruise altitude of 10,000 feet and a gradient of descent of 7% following an engine failure. Using the simplified triangle, we can work out the horizontal distance travelled by taking the height of the aeroplane above the ground, dividing this by the gradient, and then multiplying by 100. In this case, we see that in still air the airplane will cover in the glide a horizontal distance of 142,857 feet, or roughly 23.5 nautical miles following engine failure. This means that the aeroplane must not pass further away than 23.5 nautical miles from these safe forced landing locations. So we draw a circle of 23.5 mile radius around each of the safe forced landing locations as shown here. From the picture, you can see that from this point on the route to this point on the route, if an engine failure was to occur, then the aeroplane would not be capable of reaching a safe forced landing area. Therefore, if the aeroplane were to route through this point, it could not be meeting the requirements. In order to fly from airfield A to airfield B, the aeroplane would have to follow a flight path that keeps it within range of each safe landing area. If the aeroplane were to operate at a higher altitude, then it would be able to cover a greater distance in the glide following an engine failure. For example, operating at 15,000 feet instead of 10,000 feet would increase the aeroplane's still air glide range to 35 nautical miles. Therefore, the circles around each forced landing location will grow. Notice that now the aeroplane can fly along a straight track to airfield B because at all times throughout the flight, the aeroplane is within glide range of a suitable forced landing location. Consequently, small piston engine aeroplanes should be flown at their maximum altitudes so that direct routes can be achieved. However, when planning the altitude, another regulation must be borne in mind. JAROPS 1 states that when complying with the safe forced landing rule, the aeroplane must not be assumed to be flying, with the engine operating at maximum continuous power, at an altitude exceeding that at which the aeroplane's rate of climb equals 300 feet per minute. What this rule effectively does is to limit the maximum altitude that can be used in order to comply with the forced landing rule. An aeroplane may operate at higher altitude than this regulation prescribes, but the operator may not use the higher altitude in his calculation of glide range to a safe landing area. This situation is best understood by returning to our original scenario with the aeroplane at 10,000 feet and with a glide range of 23.5 nautical miles. Assume now that the 10,000 feet cruise altitude is the maximum altitude at which the aeroplane can still achieve 300 feet per minute. To comply with the rules, the aeroplane would have to fly the flight path shown. As we have seen, if the aeroplane were to fly at higher altitude, It would of course be able to glide further and assume a direct track to Airfield B. But the extra glide range achievable because of the higher altitude may not be assumed when complying with the regulations, because at higher altitude the aeroplane's climb rate is less than 300 feet per minute. Therefore, the direct track from Airfield A to Airfield B cannot be flown. The aeroplane must still fly a track which takes it within the glide range achieved at 10,000 feet. There is one last detail to be considered about complying with the forced landing rule. JAROPS 1 states that in order to comply with the safe forced landing rule, the assumed en route gradient shall be the gross gradient of descent increased by a gradient of 0.5%. In our example, we had a gradient of descent of 7%. Unfortunately though, as we have seen, the regulations do not permit this gradient to be used in our calculation. The gradient must be increased by 0.5%. This will lower the assumed descent performance of the aeroplane. The new deteriorated gradient that the regulations insist that we use is called the net gradient, and in our case this is 7.5%. If this net gradient has to be used, the glide distance will reduce to 22 nautical miles. So although the aeroplane may achieve 23.5 nautical miles following an engine failure, it must be assumed to glide only 22 nautical miles. Looking at the diagram, this means that the circles around each safe landing area must reduce to a radius of 22 nautical miles. Thus the planned track will have to change slightly, so that at all points along the route, the aeroplane is no further than 22 nautical miles from a safe forced landing area. The track now shown on screen meets the entire set of requirements as stated in JAROPS 1. We mentioned at the beginning of the lesson that the CAP manual has the en route regulations in it for you, but that they were scattered through the manual and not conveniently collected in one place. On page 1 of section 2 in the general requirement paragraph, point C is the regulation about ensuring that the aeroplane is not operated unless surfaces are available which permit a safe forced landing to be carried out in the event of engine failure. However, the other regulations about complying with this rule are a few pages further on. You will find the remaining en route requirements at the bottom of page 8 of section 2. The first part of the regulations to be found here states that the aeroplane may not be assumed to be flying above the altitude at which a rate of climb of 300 feet per minute can be achieved. Underneath that rule, you can see the requirement which states that the net gradient of descent, in the event of engine failure, is the gross gradient plus 0.5%. Although the concepts of range and endurance have been covered in a previous lesson, it is important for the pilot to be able to use the information in the aeroplane flight manual so that he may calculate the range and endurance of the aeroplane. In the aircraft manual, there are graphs and tables which help you calculate the endurance and range of your airplane under various conditions. Shown here is a typical endurance graph for a light single-engine Class B aeroplane. Let us assume a cruise altitude of 7,000 feet with an outside air temperature of 7 degrees Celsius at 65% power. The endurance of the aircraft allowing 45 minutes of reserve fuel is 6.6 hours, or 7.4 hours allowing for no reserves. The graph shown here is for calculating the aircraft range, and it works in exactly the same way as the endurance graph, except that instead of working out airborne time, distance flown is shown. To achieve these range and endurance figures, be careful to follow the techniques described in the manual, especially with regard to correctly leaning the mixture. You should have learnt two main points from this lesson. Firstly, you have learnt what the en route and descent performance requirements are that govern single-engine Class B aeroplanes and where to find them. Secondly, that the pilot must comply with these regulations when operating a single-engine Class B aeroplane in the commercial air transport category.